Go outside tonight, and I'll bet you can tell a star from a planet. No telescope, no map of the constellations, nothing. Just look up, find a bright point of light, and watch it for a few seconds. If it flickers, shimmers, trembles a little, that's a star. If it just sits there, calm, rock steady, almost boringly still, that's a planet. Every single time, no exceptions. And here's what I want you to actually chew on. How can something that simple, something you can do standing in your backyard in your pajamas, be quietly revealing one of the more delicate pieces of physics happening between you and the rest of the universe? Your first guess is probably wrong, by the way, and I say that with total confidence because it was my first guess, too, once. You look at that trembling star and you figure the star's doing something, burning unevenly, pulsing, flaring up and dying down, something dramatic happening way out there, millions of miles away. It isn't. Stars are so mind-bendingly far away and so enormous that from here on Earth they collapse down to what we call a point source, a perfect, dimensionless dot of light with no measurable width at all as far as your eye or even most telescopes are concerned. And a star's actual light output barely changes on any time scale you'd notice in a human lifetime. So whatever's making that light tremble, it's got nothing to do with the star. The twinkle isn't happening trillions of miles away. It's happening in the last 100 miles of that light's journey, right here, in our own atmosphere. So let's actually look at that atmosphere, because this is where the real mechanism lives, and it's better than you'd expect. You probably picture the air above you as one calm, uniform blanket of gas, sitting there quietly. It isn't. It's a churning, restless stack of pockets, warm air here, cooler air there, rising, sinking, drifting past each other constantly, like water just before it starts to boil. And light does something specific whenever it crosses from one density of air into another. It bends, just slightly. That's refraction. It's the exact same reason a straw looks bent the second it dips into a glass of water. Nothing mysterious, just light changing speed slightly as it crosses into a different medium, and bending because of it. Now take that single razor-thin point of starlight and send it down through dozens of these shifting, turbulent little air pockets on its way to your eye. Each pocket bends it a tiny bit, and because the air is constantly moving, swirling, rising, mixing, the exact amount of bend changes from one instant to the next. So the star's light isn't arriving on a fixed path. It's getting nudged and re-nudged, a slightly different amount every fraction of a second. That flicker you're seeing? That's not the star doing anything, that's you, watching the entire atmosphere wobble in real time, condensed down onto a single point of light, which raises an obvious problem. And I love this part because it's the part that actually explains the whole title of this video. A planet is going through the exact same atmosphere, same turbulence, same shifting air, often sitting right next to a twinkling star in the same patch of sky at the very same moment. So why doesn't it do the exact same thing? Because a planet isn't a point, it's a disk. Now, it's a tiny disk, way too small for your bare eye to actually resolve into a circle. You'd need a telescope for that. But too small to see as a circle is not the same as a single point. A planet is really thousands of adjacent points of light sitting right next to each other, each one arriving at your eye from a very slightly different angle, and each one getting bent by the atmosphere by a slightly different amount at any given instant, because they're punching through slightly different pockets of turbulent air on the way down. Here's the key part. When all those thousands of slightly wobbling points land on your eye at the same time, they average out. One point might be nudged a little left, another nudged a little right, another barely nudged at all. And instead of seeing all that individual trembling, you see the average of the whole crowd. The wobbles cancel each other out. What's left looks perfectly steady. Not because the planet's light was somehow untouched by the atmosphere, it went through the exact same turbulence the star did, but because you're watching a crowd smooth out the trembling that any single voice in that crowd would show on its own. And here's where I want to slow down, because there's something a little uncomfortable buried in this explanation if you look closely enough. We keep calling a star a point source, but that word point has nothing to do with actual size. Plenty of stars are physically far larger than any planet in our solar system, some of them almost obscenely larger, big enough to swallow our entire solar system out past Jupiter. The reason a star still collapses down to a single point from here isn't size at all, it's pure distance. Stars are so unimaginably far away that even their real physical width shrinks down to an angle far too small for your eye or most telescopes to ever pick apart into a disk. A planet only counts as a disk because it happens to be close enough, in the cosmic sense, for that averaging trick to actually work. Push a planet out to interstellar distances, out where the stars are, and it would twinkle exactly like one. It'd become a point, too. Bring a star close enough, genuinely, absurdly close, closer than any star will ever practically get to us, and it would stop twinkling completely, because now it's a disk. So the twinkle was never really a statement about what these objects fundamentally are. It's a statement about geometry, about distance, about how much of the sky each object happens to cover, standing exactly where you're standing tonight. And here's the part I don't want to gloss over, because it's the honest part. We are shockingly good at predicting this stuff. Astronomers call this atmospheric effect seeing. And if you've ever wondered why the world's best telescopes sit on remote mountaintops in places like Hawaii or Chile, it's exactly this. Thinner air, calmer air, less turbulence, better seeing. We can measure atmospheric turbulence with incredible precision. We can predict days in advance which nights will have poor seeing and which will be crystal clear. We've even built adaptive optics systems, mirrors that physically flex and adjust thousands of times per second, canceling out the atmospheric wobble in real time, so a telescope can see almost as clearly as if there were no atmosphere at all. But underneath all that precision sits something we still don't fully have a handle on. Turbulence itself, the actual transition where a smooth, orderly flow of fluid breaks down into that chaotic, unpredictable churn, is one of the genuinely unsolved problems in classical physics. We can observe it, we can quantify it beautifully, we can even engineer around its effects with real working technology. And we still don't have a complete theory explaining why turbulence forms the way it does, why it cascades the way it does, why a calm flow tips over into chaos at the exact point it does. The twinkle you're watching tonight is, in a strange way, sitting right on top of one of the oldest open questions physics has never fully closed. So here's what I actually think is going on every time you look up and pick out a star from a planet without even trying. That flicker isn't a flaw in the universe. It isn't a flaw in your eyes either. It's a message, written in real time in the trembling or the stillness of a single point of light, about how far away that object actually is, translated through 100 miles of restless, breathing air sitting right above your head. The steady planet and the trembling star are going through the exact same physics. The exact same turbulent atmosphere is doing the exact same thing to both of their light, at the same moment, in the same patch of sky. The only difference between them is distance, and distance alone is enough to turn identical treatment into two completely different experiences. Maybe that's the real thing worth carrying away from something as small as a twinkle. How much of what looks like a difference in kind between two things is really just a difference in distance, in scale, in how much of something ever reaches you at once, and whether that arrival comes as one lonely, trembling point or as a crowd large enough to steady itself out? And how the universe, without meaning to, without any intention behind it at all, hands you a way to read that difference every single clear night, for free. No equipment required, just by looking up and noticing quietly which lights hold still.